So this one, problem of the day, 120, 125, 23, first one. Draw the mechanism showing the electrophile activation and the electrophilic aromatic substitution below. So what I'm asking for here first is to do the electrophile activation, how to make it super electrophile. So what needs to happen, you draw your lone pairs in on your chlorine, and it's going to go to the aluminum. And what that's going to form is this. And you must include these steps. And then this isn't happy, so this is going to generate a carbocation. This is the Friedel-Crafts alkylation. And yes, you need to balance your charge every time. Alright. So we make a carbocation. Now we got to worry about rearrangements. So this is a tertiary carbocation. So the only way I can make this more stable is having pi bond or lone pair resonance. And I don't see that as a possibility. So I'm done. Now, at this point, I'm given the product here, but I also could notice, right now I'm kind of done. I've done that. I've done the activation. Now I need to do the electrophilic aromatic substitution. So I need to look at the groups on the ring. And in this case, I'm given the products. So the group that's adding is adding para to the sulfur. So the sulfur group is actually a electron donating group, has a lone pair next to the ring. So the sulfur, nitrogen, phosphorus, and oxygen are all donors. And you're being told the group is adding para, right? Probably because this is very big. The other place it normally could add is ortho into the sulfur group, but because this is a big group, it's bulky, sterics is going to add para. But you're told that. Okay, so what needs to happen is the H that's in the para position has got to go, right? Substitution reaction. We're going to substitute this H, which ends up being this H, with the terbutyl group. So the first step in the actual electrophilic aromatic substitution, now the activation, is the pi bond reacts. So which pi bond does it have to be? It has to be the pi bond here, right? Why does it have to be that pi bond? Because we need to add the group to this carbon, so we need to have the carbocation here, so we have to use this pi bond to have it add. If we were adding ortho, we'd use this pi bond, or we could use this pi bond, right? So we need to use the pi bond that is the position we want to add the new group. So we add it, right? That's the addition step. Right, that's going to be the slow step always. Talked about that a lot, right? Why is that the slow step? That's the slow step because we're making the carbocation then. And we're also breaking aromaticity, right? Right? Now, in the past, there are different types of questions. I've also said, okay, this is a sigma complex, right, or an intermediate, and you can draw resonance structures of these, right? You can always draw at least 3, and then sometimes you can draw 4. But I didn't ask for that here. I just asked for the mechanism, right? Usually I'll try to be very clear if I ask for that. So now we've done the addition. Now we need to do the elimination. So the elimination is we got to regenerate the catalyst. So the electrons in the bond between the aluminum and chlorine. We're going to take the H. We're going to do this like E1, right? Elimination. We're going to get the product. We're going to regenerate the catalyst. Oops, sorry. We're going to regenerate the catalyst. All right, AlCl3. And that H we took off is now there with the chlorine. And this will be a fast step because we're re-aromatizing.